Welcome. In this differential equations tutorial, we're going to look at systems of nonlinear differential equations. And so we're not going to focus on solving those. We're going to focus on looking at the long-term behavior of those systems. Okay, so let's get started here with question 1. Now, in question 1, we have a linear system, but it's not homogeneous. So we have x dash equals x plus 2y plus 3, and y dash equals 4x plus 5y plus 6. Okay, so the first thing that we want to do is find the critical point of the system, and this occurs when x dash is equal to 0 and y dash is equal to 0. And so we can see that this corresponds to x plus 2y equals minus 3 and 4x plus 5y equals minus 6. Okay, and so we can solve this. Now, I'll take a matrix approach here because if I have the matrix A given by the coefficients of the x and y there, 1, 2, 4, 5, then the inverse of A is 1 over the determinant of A, so 5 minus 8 is minus 3. And then I take the 1 and the 5 and I swap their positions and put minus signs on the 2 and the 4. Okay, and so x star, y star, our critical point, is equal to A inverse times minus 3 minus 6. And so we have 1/3 5 minus 2 minus 4, 1 times 3, 6. What I've done with the minus sign is I've brought it through all the way to these minus signs so that the product gives positive numbers, which I think will make the calculation a little bit more clear. Okay, so let's multiply this out. We've got 1/3. 5 times 3 is 15. So 15 minus 2 times 6 is 12. And then we have 6 minus 12 in the bottom row. Or minus 4 times 3 and 1 times 6. So this gives us critical point equal to 3 over 3 is 1. And then minus 6 over 3 is minus 2. Okay, so we have found the critical point of the system. Next, we want to classify the stability of the system. So to do that, we just look at our matrix A, take the trace of A. So that's the sum of the diagonal entries. So that's 1 plus 5, which is 6. Now that's positive. Let's calculate the determinant of A. That's 5 minus 2 times 4 is 8. So 5 minus 8 is minus 3. That's negative. And so now if we look at our stability chart, which I'll bring up right here, we have a positive trace and a negative determinant. So that's in this fourth quadrant. So we have a saddle for this system. So we'll classify as an unstable, because all saddles are unstable, saddle at the point 1 minus 2. Okay, let's move on to question 2. Consider the non-homogeneous linear system. Well, that's the same one. Use differential operators to solve this. We have x plus 2y plus 3. Y dash equals 4x plus 5y plus 6. Okay, and so I want to write this, putting the x's with the x's. D x minus x equals 2y plus 3. And so I can express this as d minus 1 x equals 2y plus 3. Now for the second equation, I can express that as d minus 5y equals 4x plus 6. Okay, now applying the differential operator d minus 1 to both sides of the second equation, so that gives us d of 4x plus 6 minus, in brackets, 4x plus 6. Okay, now this says to differentiate this. And so we're doing that with respect to t here because d represents, take the derivative with respect to t. Okay, so this is 4x dash plus 0, and then we have minus 4x plus 6. Okay, and so this is 4 outside of d minus 1 applied to x, and then plus 6. Okay, so now what we can do is take this d minus 1 of x and sub that in there and get a differential equation that is second order. And that's what this process does. Okay, so we have 4 times, in brackets, 2y plus 3, and then plus 6. And so if I expand that, I've got 8y plus 12 plus 6 is 18. And then on the left-hand side, expanding this, we have d2 minus 6d plus 5 applied to y, which we can write as y double dash minus 6 y dash plus 5y is equal to 8y plus 18. So subtracting 8y from both sides, we have y double dash minus 6 y dash minus 3y is equal to 18. Okay, so now I have this second order differential equation to solve. It's not homogeneous. So what we do is add the homogeneous to the particular solution to get our general solution. Okay, so let's come along here and finish this off. So the characteristic equation is lambda squared minus 6 lambda minus 3 equals 0. Okay, so lambda equals 6 plus or minus the square root of 6 squared is 36 minus 4 times 1 times minus 3. And that's all over 2 times 1. So we have 3 plus or minus 1/2 of the square root of 36 and 12, which is 48. And 48 is 16 times 3. The square root of 16 is 4. 4 over 2 is 2. So we have 3 plus or minus 2 root 3 for our two eigenvalues, or solutions to the characteristic equation. Okay, so now we know what the solution to this looks like in the homogeneous equation anyway. So y homogeneous equals a e to the 3 plus 2 root 3 times t plus b e to the 3 minus 2 root 3 times t. And now we'll guess y particular equals, say, lowercase a, because this right-hand side is a constant. Now differentiating that, we've got yp dash is 0, yp double dash is also 0. So subbing these into this differential equation right here, what we get then is minus 3a is equal to 18. And so lowercase a is minus 6, which is 18 divided by 3. Okay, so given that, we add this, which incidentally is our yp. We add yp to the homogeneous solution, and we have our general solution. Y is equal to ae to the 3 plus 2 root 3 t plus b e to the 3 minus 2 root 3 t minus 6. Okay, now given that, can we use that to find x? Well, yes, we should be able to. So if we just look at the first equation we have here, and we sub this in for y, then we should be able to find x, okay? But I would rather move on here. Okay, so let's move on. All right, so question 3. A pond initially contains x equals 3 carnivorous piranha. So x of 0 is 3 piranha. And y of 0 is 12. I'll just call them yellows. So electric yellow cichlid. They have babies in their mouth, which is fun to pull out. You pull them out with a paper clip once they're ready. Okay, so the system is governed by the equation, or system of equations. X dash is 3x minus 4xy, and y dash is xy minus 9y. Determine critical points of the system. Well, these occur when x dash is 0 and y dash is 0. Okay, and so we want to solve the system of nonlinear equations 3x minus 4xy equals 0, xy minus 9y equals 0. Now this is a simultaneous system of nonlinear equations. Okay, and so what we want to do is carefully and logically consider all the cases. So take the first equation. Let's label this equation 1 and equation 2. Now in the first equation, we can factorize an x out. So equation 1 gives x outside of 3 minus 4y equals 0. Okay, and then equation 2 gives y outside of x minus 9 equals 0. So let's separate some cases. Case 1, x equals 0. So that's one way to have 0 there. So if x is equal to 0, then what we have is 0 there. So we have minus 9y equals 0. And so y would be equal to 0, and we get a critical point, 0, 0. Okay, now case 2, the only other possibility for equation 1 is y equal to 3/4. Okay, from this being equal to 0. So if y is equal to 3/4, then what we have is we must have x minus 9 equal to 0. So x would have to be equal to 9. Okay, since those are the only two possibilities for the first equation to be satisfied, we have two possible critical points. So the critical points are 0, 0, and 9, 3/4. Okay, so we have found the critical points of the system. So next, we want to calculate the Jacobian matrix at each of our critical points. So I write the Jacobian matrix like this: J, F at the critical points, something like this. So we have F subscript X at X star, Y star. We have F subscript Y at X star, Y star. We have G subscript X at X star, Y star. And we have G subscript Y at X star, Y star. Okay, so here's our Jacobian matrix where F of X and Y is equal to X dash, which is 3x minus 4xy. G of X and Y is Y dash, which is xy minus 9y. Okay, so if we are taking partial derivatives with respect to X and with respect to Y for each of these functions respectively, that's what we want to do here. So Fx is the partial derivative with respect to X of F. And so we're differentiating partially 3x minus 4xy. So we have 3 and then minus 4y for that. Okay, F subscript y is the partial derivative of F with respect to y. And so for that, we have the derivative of 3x with respect to y partially is 0. So 0. And the derivative of minus 4xy with respect to y partially is minus 4x. Okay, and then gx, differentiating g partially with respect to x, we get y minus 0. So just y. Okay, now g subscript y is equal to x minus 9. Okay, now we put all of these together in our Jacobian matrix. And so we have 3 minus 4y. Then we have minus 4x. Then we have y. And then we have x minus 9. Okay, now we want to sub in each of our critical points. So J at 0, 0 is the matrix 3, 0, 0, minus 9. Okay, similarly, j at the point 9 comma 3/4 is subbing in 3/4 here. We have 0. Subbing in 9 there, I have minus 36. Subbing in 3/4 there, I have 3/4. And subbing in 9 there, we've got 0. Okay, now we should use these two matrices to classify the critical points using our stability chart, which is this right here. Okay, and so I'll come to a new page. So the trace of A1, where this is A1, let's call this A1, and we'll call this one here A2. So the trace of A1 is 3 minus 9, which is minus 6. That's negative. The determinant of A1 is 3 times minus 9 minus 0 times 0. So we've got minus 27. That's negative. So we have an unstable saddle. At the critical point 0, 0. All right, now for the second critical point, the trace of A2 is 0 plus 0, which is 0. The determinant of A2 is 0 minus 36 times 3/4, which is, now 36 divided by 4 is 9. So we have 9 times 3 plus 27. That's positive. Okay, and so let's look at our stability chart here. We have a 0 trace. So we're on the determinant axis, 0 trace. And we have a positive determinant. So we're somewhere on the positive end of the determinant axis. And that's called a center. So the point 9 comma 3/4 is a center. So we found a saddle at 0, 0 and a center at 9 comma 3/4. Okay, so let's open up Mathematica now and plot this, and I'll show the two of those to you. So we'll plot this with stream plot. So I'm going to change this to X and Y. So the first one is (3x minus 4xy), and then we put in our second one, y dash, which is xy minus 9y. Okay, and now I will press Shift and Enter. Now I want to take this from, as x goes from, say, minus 0.1, just beyond. So we've got to go beyond the 9. So let's go to 12 or so. And then the y from minus 0.1 or so up beyond the 3/4. So let's take that at least to 1 or 2. All right. And so I can see, well, there's a center there where I expect at 3/4 or 9,3/4, and down here is a saddle, but what we want are more trajectories to be shown here, right? So I should go in the options and add more trajectories, but let's just take the x down to 10. Maybe we'll get some more. Okay, and I'll take the y's from 0 to 1. So you can kind of get a rough idea here of what's going on. So we have a saddle here at 0, 0. So if we had an initial condition that started where my mouse is, that would say that the number of electric yellows would decrease in population, going down, while the number of piranhas increases, and then eventually it would come up, and those population numbers would oscillate around the center. Okay, so let's move on now to the next one. So we've classified the stability of the linearized system. That was the stability of these two critical points. We've done that. Okay, the next part is determine the long-term behavior of the system. We've done that by saying what happens. The two populations will oscillate around this 9,3/4 population. Okay, so let's move on now to question 4. Consider the nonlinear second order differential equation x double dash plus mu x squared minus 1 x dash plus x equals 0, which models the van der Pol oscillator circuits for radios where mu is positive. The system exhibits a limit cycle, which is a periodic solution. Determine the critical points of the system. Okay, so first we need to couple this system. So we'll let y be equal to x dash, so that y dash is equal to x double dash. And so then that there is y dash. So y dash plus mu times x squared minus 1. X dash is y plus x equals 0. Okay, so we want to take these two terms over to the right-hand side of the equation. Y dash equals minus x minus mu x squared minus 1 times y. And then above that, we will write x dash equals y, which is just this line written in reverse order. Okay, great. So now let's find the critical points of this system. So critical points occur when x dash equals 0 and y dash equals 0. So we can clearly see from the first equation that we must have y equals 0. And so if we have y equals 0, then we must have also, subbing that 0 in there, if this is equal to 0, then we must also have x equals 0. So 0, 0 is the only or unique critical point of that system. Okay, so we've done part A. Now calculate the Jacobian matrix at the critical points. Well, there's only one critical point. We know that. So let's let the top line be F, the second line be G. And so we want to take F subscript X, the partial derivative of F with respect to X, but F is Y, and so this is 0. Now, f subscript y is the partial derivative with respect to y of f, which is y. And so this partial derivative is just 1. Okay, g subscript x is the partial derivative with respect to x of all of that minus x minus mu x squared minus 1 times y. And so minus 1 for the minus x. And then we have minus mu y partial derivative with respect to x of x squared minus 1. Now we can treat the mu and the y as constants because we're taking a partial derivative with respect to x. Okay, now the derivative of x squared with respect to x is 2x. The derivative of minus 1 with respect to x is 0. So we just have minus 1 minus 2 mu x y for g subscript x. All right, now for g subscript y, we have the partial derivative with respect to y of minus x minus mu x squared minus 1 y. And so 0 for this. These two can come out the front of the operator. And so the derivative of y with respect to y is 1. So this is our derivative there. Okay, so we want to take these now and place these in a Jacobian matrix. Except I need more paper, so I better grab some. All right, so J F equals Fx 0, Fy 1, Gx minus 1 minus 2 mu xy, and Gy is minus mu x squared minus 1. Okay, now let's sub in our only critical point, 0, 0, in for x and y. And so we have 0, 1, 0 there, so that's minus 1 down here. And then we have minus mu times minus 1 is plus mu. So there's our Jacobian matrix. Okay, and so now the trace of the Jacobian matrix is 0 plus mu, which is mu, and that's positive because mu was said to be positive at the beginning. Okay, now the determinant of this Jacobian matrix at the critical point 0, 0 is 0 times mu minus 1 times minus 1. And so that's plus 1. That's positive. Okay, so now we know that the matrix lies in the first quadrant of the stability chart, which I'll show you again. So the first quadrant of this chart, so what we need to do is decide, is it on this side or is it on this side of the curve? Determinant of A is 1/4 the trace of A squared. All right, so then we need to calculate 1/4 trace of A squared, or J in this case. Okay, so that's 1/4 mu squared. And compare that against the determinant. So what we learned then is if 1 is greater than 1/4 mu squared, then what we have is an unstable spiral. At the critical point 0, 0. But, and so this is equivalent to mu squared is less than 4, which is equivalent to, since mu is positive, mu less than 2. Okay, and so let's look at another case. So if, on the other hand, 1 is equal to 1/4 mu squared, and so what this case is mu exactly equal to 2, then we have an unstable proper node at the critical point 0, 0. Okay, and our final case, if 1 is less than 1/4 mu squared, then we are under this curve right here, and so we would have an unstable node. Okay, so this is equivalently mu greater than 2, then we would have an unstable node at the critical point 0, 0. Okay, so now let's get on Mathematica and give a plot of the phase portrait. Okay, so we need to put in, so we've got x dash is y, and y dash is minus x minus mu. I'll just write m for mu instead. In brackets, x squared minus 1 times y. Yes, okay. So if I give m a value, say something, what did we say? Less than 2, m equals 1.0, for example. Let's try this. And then we need to bring back our plot range down to, say, 2. Okay, and let's give some negative values as well. Okay, so we have an unstable spiral there at 0, 0, exactly as we predicted. All right, now let's choose a value that is greater than 2, say 3. And now we have an unstable node at the critical point 0, 0. Okay, so at 2 itself, we should have a proper node there near that critical point 0, 0. So there's a proper node there. And now what I'm going to do is clear all of those mu values, and I will write manipulate. And we will manipulate over m as m goes from, say, 1 to 3. We should get a slider bar here. Okay, I'll make this bigger, bring this in smaller, and then we'll slide this over. Okay, so this should be the smallest mu value we selected. So let's see how these change. Goes from an unstable spiral as we increase mu to an unstable node. Okay, so let's do that again. Here we've got an unstable spiral. Somewhere we hit mu equals 2, and we get an unstable proper node. Looks like it could be happening around here. And then we get, after that, we have an unstable node. Okay, question 5. We have two competing species. whose populations are negatively affected by their interactions. Okay, so let's first find our critical points. Actually, I should first read the question. What do you expect to happen to the populations X and Y over the long term? Well, one of them might die out, for example. We'll see. Okay, let the carrying capacity N of the population X be equal to 4. Find all equilibrium points for the system. Is there an equilibrium where the populations coexist? All right, well, let's see whether we can solve this in terms of N first, and then we can sub in N as 4. So critical points, again, these occur when X dash is equal to 0 and Y dash is equal to 0. So we have then X, for the top one, I'm seeing that there's a common X I can factor out. X outside of 0.2 minus 0.2 over N times X plus 0.1 Y. Okay, I can see that there's a common Y here in the second equation. So I'll pull that out. And so we have 0.6 minus 0.6 over 3 times Y. And then we have plus 0.05 X. Okay, now let's separate cases very carefully. So case 1, if X is equal to 0, then I would get 0 in the first equation, and subbing that into the second equation, then we have Y times 0.6 minus 0.6 over 3, which is 0.2 Y, and then 0 here, so this equals 0. So that shows us two possibilities for the Y when X is 0. So Y equals 0, or Y is equal to 0.6 divided by 0.2, which is 3. Okay, and so this gives rise to two critical points, this possibility. So 0, 0, or 0, 3. All right, now case 2, or other possibility for the first equation, we could have 0.2 minus 0.2 over N X plus 0.1 Y equals 0. And so if we have that, we could have then Y equals 0 in the second equation, or this equals 0. Okay? So if Y equals 0, then we get 0.2 outside of 1 minus 1 on N times X is equal to 0. So X would have to be equal to N. And we get the critical point N, 0. Okay, now if in the other case we have 0.6 minus 0.2 Y plus 0.05 X equals 0, well, then we have to solve these two equations simultaneously, and that would give us our last possible solution to this system. Okay, so let's go ahead and do that. Now, I think just to make this easier, I'll just get Mathematica to do that part. I'll open this up. And so I'll type in those two linear equations. So we have minus 0.2 over n brackets x plus 0.1 y equals minus 0.2. That's our first equation there. Then the second equation, I'll write 0.05x minus 0.2y equals minus 0.6. Okay, let's put brackets around those. And then I will just want to ask it to solve this for x and y. All right, and so now we have our last possibility. We have another critical point. Let's see, how do I want to read this? Minus 20n over n minus 8, comma, and then over here we have minus 2 outside of 12 plus n over n minus 8. And I should go with uppercase here to be consistent. Okay, yes, that looks correct. All right, and so this is our fourth possibility. So we have this one, we have these two, and we have this. All right, now, since n is equal to 4, we're told in the question, we can simplify these. We have the critical points 0, 0, 0, 3, 4, 0, and then the last one becomes minus 80 over 4 minus 8 is minus 4. So minus 80 over minus 4 is 20. Yes, okay, and then up here, 4 plus 12 is 16, so minus 32 over minus 4 is 8. So these are our 4 critical points for that system when n is equal to 4. Okay, now the question says, is there an equilibrium where the populations coexist? So what we need to do to decide this is determine whether any of these have some kind of oscillating, something like a center. So that's called a limit cycle. Are any of these limit cycles? Now, if one is a saddle, then there could be trajectories where one of the populations goes to 0 and the other population goes to infinity. Okay, but we're going to need to evaluate the Jacobian matrix for this system. And so I'm going to get some Mathematica help here to do that. So come back to this, and I will write in f is equal to, I'm just going to copy this because I've already typed that. And then I will take this over to the left-hand side. So f is that correct? Not quite, is it? No, so I need to retype this. 0.2x, and then we have 1 minus x over 4. Okay, and then plus 0.1 x times y. You can see that I need to clear the x values. Okay, let's enter g. So I'm entering the second line there. 0.6 y, 1 minus y over 3, and then plus 0.05 xy. Okay, so there's f and g. Now let's differentiate each of these partially. Differentiate g with, f with respect to g, with respect to y, sorry. Okay, so I am now forming the Jacobian matrix. Okay, so there we have our Jacobian matrix symbolically. And then what I want to do now is replace. So this slash dot means replace all. So I'll say x goes to 0, y goes to 0. So this will give me the Jacobian matrix at the critical point 0, 0. Okay, and so call that A1 is 0.2000.6. And that's at 0, 0. Okay, then we have A2. Let's do the same thing for that. So 0, 3. So 0.5, 0, 0.15, and minus 0.6. Okay, so next, let's do the same thing for 4, 0. So A3 minus 0.2, 0.4, 0, 0.8. And this is at 4, 0. And then finally, A4, we sub in 20 and 8. And we get minus 1, 2, 0.4, and minus 1.6. 28. Okay, now we can classify each of these. So the trace of A1 is 0.8. The determinant of A1 is 0.2 times 0.6, which is 0.12. Okay, so positive and positive. So we have more work to do on this one. All right, so at this, we have trace of A2 is minus 0.1. And the determinant of A2 is a negative number. So it's minus 0. Is it 0.3, I think? Yes, minus 0.3. All right, so this one is a saddle. So it's unstable. All right, 4, 0, we've got a trace of A3 equal to 0.6 and determinant of A3, the product of these two, because we have a 0 there. So it's negative, it's minus 0.16. Okay, and then finally 28 the trace of A4 is minus 2.6. The determinant of A4 is 1.6 minus 0.8. And so that's plus 0.8. And so we have a little bit more work to do to decide what this is. All right, so let's go back to, okay, so this one was a saddle as well, A3. So these two here were saddles in our classification. And so 0, 0, we have a little bit more work to do. So 0, 0, 1/4 the trace of A1 squared is equal to 1/4 of 0.64. And so that should be 0.16, which is the greater one than determinant of A1. Okay, and so I think that this should be, according to the stability chart here, let's see, we have a positive trace and a positive determinant, but the trace is the bigger one. And so I think that that should be an unstable node. At 0, 0. Okay, and now to classify the critical point 28, 1/4 the trace of A4 squared. Now 2.6 times 2.6, let's have a look. So 6.76, and then we need to divide that by 4. So we get 1.69 for that. Okay, so we need to compare this against the determinant 0.8. So trace is quarter, the trace squared is the bigger one. So this is should be a stable node because that trace is negative. Trace is the bigger one. Okay. Yeah, so I believe that this is a stable node. Okay, so let's go to Mathematica now and stream plot this. So where did the equation go? Okay, so I should just be able to put stream plot f comma g. So we'll come down here, put this in. So I'll put f, and then I'll put g, and then we'll also set, yeah, we've already set n equals 4. Okay, so I should be ready to go here. But we need to extend our range to include these critical points. So let's see, we had 4 critical points. The biggest one was 28. So let's go, x goes from -2 to, let's go 24. Y goes from -2 to 10. Okay, so this should include all of them. So we classified 0, 0 to be an unstable node, and that's what that looks like there. Okay, then we have 0, 3, so that'd be up here, a saddle. Yes, that's what that looks like. And then 4, 0, that's a saddle. And then way over here at 28, we classified that to be a stable node. And that is what that looks like there. So they're coming towards that point 20, 8. Okay, that does it. Thanks.